He's working as a data scientist at Mars. And he's also part of the organizing committee, actually. And as far as I know, the only one who reviewed all proposals. And there were a lot of proposals. But mostly he's very passionate about the topic of conformal predictions. He's doing a PhD in the area at a university in Cyprus. And yeah, so therefore the quality of the talk is guaranteed. Please welcome on the stage. Welcome him on the stage.
Hello, everyone. I see a lot of people. I see some smiles as well. Thanks for the introduction. I hope you had an amazing morning. So today, I'm here to talk about a fundamental shift, which I really believe that is a fundamental shift. And as mentioned, we're going to move from point predictions, which we hope are right, to a prediction set, which is statistically trusted. The talk, given the time, is from a classification standpoint, but the method that I'm going to propose can be used, can go beyond to a regression setting. Kicking off, I think you can all read the title, but imagine that we have a data set which includes animal pictures, all the way from dogs, cats, sheep, you name it. And we want to classify animals given a picture. So right now, we can see that all of us, of course, can understand that this is clearly a dog, and a classifier will give a very high probability that this is a dog. However, if we introduce a bit of noise in the image, and we show a picture like this to a classifier, then, of course, all of us would say that the classification outcome would be less certain. So we're also less certain that this is a dog. Dogs are fun, and animals in general, and I love them, don't get me wrong, but because we're talking about such a method and such an approach, let's take this a bit further. What about CT scans? They're all around you. You will see CT scans on LinkedIn because it's a very risky application. You'll see them on Google in papers. What I want to highlight today is we have an image from a CT brain scan that I found from Physiopedia. And let's say that we have a data set again with a lot of labels and individuals being healthy as a disease as a label or having a specific type of stroke. Same example that we want to classify if this individual is healthy or is having a certain type of stroke or a brain tumor. Now, we put this into the model, and the model comes back, and the output of the model is the most likely class, hereby saying that this individual is healthy with 90% probability. Although, imagine you're a doctor and you see this 90% probability, I think you're biasing yourself to say this individual is healthy, and you will, of course, justify and evaluate the model. If we empirically test every model outcome, which says it's 90%, and we ask the question, is it actually 9%? We actually can see that most models are uncalibrated, which means although they say it's 90% probability that this is the case, there's only 50% of the outcomes that this is happening. That's what we say a model is uncalibrated. In practical terms, to give an example of the output of the consequences of this, it would be if the doctor trusted this with 90% score, they might dismiss a patient which actually needs care, which comes with a huge cost. Sticking to the same example, I'm going to reformulate the example so you can think along. Imagine the model says ischemic stroke, which you might not know what it is, and it's a certain type of stroke. How would you act as a doctor? I think you would evaluate, you would see if the individual is having a stroke or if he's having a specific type of stroke. How different would your chain of thought be if the model would give you a prediction set, which is guaranteed to have the answer 90% of the case, and this coverage is defined by the user, be it the data scientist or the doctor, and it would say, it's either healthy or ischemic stroke or a brain tumor. So in other words, the model is saying, I'm uncertain, so I'm giving you a set of classes with 90% certainty that it's going to be one out of the 3 as a true label. That's what today's talk is about. So it's not about point guesses, but unbiased uncertainty guarantees, even when the data are imbalanced, because most of the data are imbalanced and the data quality is not the best in real life. Please have a food for thought the question, and we turn the question from did we catch the disease to a question of like, how honest is our model about what it doesn't know? I think you know enough. I'm just kidding. I'm just calibrating my training set. So actual talk. I don't want to stand a lot in this talk. I'm Konstantinos. I work as a data scientist, I think as most of you here. And I have a particular interest about uncertainty quantification. I see it being all over my life. And I've been trying to address it through a conformal prediction, which is a very new, maybe not new, but maybe popular the last couple of years. I'm going to abstract the example I gave you before, and I'm going to abstract it in a way to say model outputs just give you the most likely case, just return the most likely case. You can also see the probabilities, of course. But although they are bold and they give you direction, so they say, oh, it's class A, you can act on it, it can be dangerously overconfident, as we saw before. Now, look at the prediction sets that I have on the screen right now. They give you 3 prediction sets. Instead of one answer, you get a set of plausible labels. Our model expresses its uncertainty by saying it could be either class 1, 2, or 3. And we're not 90 sure if it's class 1 or 2 or 3, but we're 90 sure that the true label is somewhat inside this set. So that's the confidence guarantee that the user defines. This is a fundamental shift. I'm saying the same sentence again that I have on my head, because the probability right now isn't about the specific label anymore, but it's about the reliability of the procedure we use to create this set. I want to highlight this thing, which says it's guaranteed coverage. A lot of people misinterpret it, so I'm trying to clarify this, that this doesn't mean that each individual prediction region, and by prediction region I mean this set of classes, has a 90% probability of containing the true outcome. But if you have 10 prediction sets, you can expect 9 out of 10 to be the case. In the next class, it will be 10 out of 10. In the next class, it will be 8 out of 10. So that's what we define as marginal coverage. So for the whole set, this is on average guaranteed. This method, conformal prediction, is giving you a mathematical proof that this is actually going to be the case. I want to skip to, I jumped too soon. I want to skip to how does this fit into the process diagram, which is, I've been talking about conformal prediction and its benefits, and then it's guaranteed in 4 minutes, which is a lot of dense information, I can imagine. How does that fit into the process? So conformal prediction, which I'm going to touch base in a couple of slides, is just a wrapper that you wrap around your model. And the first process that I'm pointing on the screen with the pointer is I took the MNIST data set. I just took the MNIST data set with a couple of numbers. You put it through a logistic regression, so this part stays as is. Of course, you do your feature engineering, your EDA. So this part stays as is, and conformal prediction comes on top as a next step to wrap your model and to actually calibrate your outcome. The output of conformal prediction, as I saw before, is for classification, is a set of classes. You can see that we named a prediction set. Now, okay, I've been talking about conformal prediction, and it's that it's so fancy, so nice. You hear mathematically guarantees. You're like, oh, yeah, okay. But okay, let's see what does conformal prediction has to bring to the table. And in the end of the day, with what are we benchmarking? What are the other methods? Why should one use conformal prediction? What have we been using until conformal prediction? So conformal prediction, as you can see, is distribution free, which makes no assumption about the underlying data distribution, which makes it incredibly robust for real-time data, which are messy. It's a wrapper, as I said, and by wrapper I mean that it's model agnostic. So it can work on top of any model which is out there. Lastly, named it a lot of times, it gives you mathematical guarantees. And unlike asymptotic methods that only promise to work with infinite data, conformal prediction actually provides a provable mathematical guarantee on your coverage with finite data sets that you use today, because your data is not infinite. However, all of this, just like the atlas we see on the screen, stands on the shoulder of exchangeability. A lot of people in this room may have heard this before. So I have for the people who haven't heard this before, I have a specific slide. So you can think of exchangeability as a softer version, or as a more flexible version of IID, independent and identically distributed. Now, what does that mean is that your data should be suffable. So we have 3 sets that I'm going to name in the next slide, which is train, calibration, and test set. If your test set doesn't look like your calibration data, then your confidence guarantees just don't hold. So exchangeability means that the data is suffable, there's no hidden order or time dependencies. And please highlight the word time dependencies, because a lot of people might do forecasting right here, which is, of course, time dependent. And I'm going to give an example to make it a bit easier. I'm sticking to the MNIST data set. So again, there's a couple of digits that we see on the left side. This is my calibration set. And of course, assume that we have a training set of, let's say, 50,000, 100,000 digits and a calibration set. You can see that this is my test set. So although I see 6 on the left and 6 on the kind of middle of the screen, right here, they come from the same, they look the same. They're not different in a way which is somebody just drew a 6. So these data are exchangeable. And another example to continue on this would be, I'm sticking to the same data set, and there is a guy just going on Word and just writing numbers. Of course, these data are not exchangeable because you train your model on the handwritten digits of MNIST, and then you test on like a digital font. This would never work. Now, let's take a step back, and let's, what I have on the screen right now is for classification, how conformal prediction actually work. So this is not black magic. It works as I'm going to explain, but before that, I want you to think conformal prediction as a blueprint. And what I mean with the blueprint, I mean as a recipe. I don't want you to think conformal prediction as an algorithm, certain type of steps, you apply them. We have what's new in conformal prediction, what's different in conformal prediction is the calibration set, and this is where magic happens. So you have you're training your model on your trend set, and then you use that to actually calculate the non-conformity scores. For every example in the calibration set is exactly that we ask the model to predict what is a true label. And then what I named non-conformity score is just a way to answer a question like, how surprised was the model by the correct answer? So how non-conforming is the new point that I see based on the set that I have on the training set? We sort the score that we see from most certain to uncertain, but I don't like to stick there. And the user has actually the ability to choose a confidence level and find the threshold. This is a key step because it gives you the opportunity to, in a way, trade off your certainty or uncertainty with a confidence level that you got input to the model. Next up, we choose a threshold. So we're saying in our calibration set, we see 90% of the true labels had a subscribe score less or equal to Q hat, which is the threshold that we see. We assume that the new data will behave similarly. So please stick to that. And that's how we define a threshold on the calibration set. Now, on the test set, this would look the same. So we compute the non-conformity scores for the new data points, we select all labels, and for this label, we construct a prediction set. What I want to emphasize again is that please think of conformal prediction as a recipe, don't think it of an algorithm, and I'm saying this because You, in literature, you're going to find a lot of different ways to do conformal prediction. So it's a universal method. And the biggest differentiator there is in the papers that have been out is nonconformity score. The most classic one being an absolute error or a log loss for classification. But you can please use your imagination in a way to use different nonconformity scores. This way you can change your conformal predictions. There are others who just optimize for different goals like smaller sets or better condition coverage. Thankfully, to a lot of people that we have in the community, we can actually use any of these libraries in Python. I'm sticking to Python. This is PyData Amsterdam. We can use any of these libraries to actually use conformal prediction in a very simple way. I use the word very simple way, so please join me in seeing that in 4 lines of code, I'm actually implementing what I've been speaking for the last 14 minutes. So in 4 lines of code, I have the ability, with a couple of arguments and the confidence level that I'm defining, to calibrate my outcome. This is amazing. Of course, it's a blessing and a curse because you may need conceptual knowledge to come or to debug something like this. But it's amazing in the way how abstracted it is. The next slide is about an example that I want to take. I want to show you an example of, OK, let's make it practical kind of way. I've been talking about this for long now. Let's make it practical. I stuck to the MNIST dataset because I said it's easy to interpret. I think everybody here knows it. If not, it's a very famous dataset. It's been used for many different reasons and benchmarks. It contains images, 10 classes from 0 to 9, and an image corresponds, a class corresponds to the handwritten digit of the image. Class 0 is the number 0, 1 is the number 1, and so on and so forth. The example that we have on the screen is that I have the distribution between the classes, which you can see the data are mostly balanced. The only difference that I see is the digit 5, which is 9%, but everything is mostly balanced. What I'm going to do is that I'm going to fit a classifier, whatever that may be, and then I'm going to fit a random, and a conformal predictor on top of it to showcase the difference in the outputs and to showcase why this is important for us in a practical manner. So I did what I did. I applied a classifier, and I took a random example from the test set, which happened to be the number 4. You can see on the left side of the screen in here that the point prediction output from the classifier of the conventional one is just 6. Apart from the fact that it's terribly wrong, which is fine, it's completely uncalibrated. It doesn't give you any guarantee, any sort of like coverage that this is going to be the case. So you see 6, but you don't know how to trust this and if you can trust it. The only evaluation metric we use is the classic classification metrics. Where on the other hand, on the right-hand side of things, you see a conformal prediction set, which is small, and we want it to be small, because if I showed you 4 numbers here, you'd be like, oh yeah, but what should I use? So it's small, it happened to be small, and it says with a 90% confidence level, it's guaranteed that this picture is actually the number 4. So stick to what I'm linking to what I said in the beginning, that marginal coverage is on average true. This is on average going to be a 4 number. Please take this with you. Imagine that guarantees are very important, because although we as humans like to have a point predictor, which gives you direction, so it's very actionable as an insight, it doesn't really give you guarantee that comes with it. So it's a trade-off of, do you want an illusion or do you want something like at least proven? Now, I played around with it a bit. I couldn't stand with just giving you only a balanced example. So I said, okay, let's strip away all the digit 5 class. Let's make this problem a bit difficult. Let's make it imbalanced. Let's make it real-world data set as much as I can. You can see that in the middle of the screen, we see class 5 is only 0.2%. compared to everything else, which is around 10, let's say. I want to bring our attention back and our focus again to what I said, which is marginal coverage. It's on average true. And I did the same step of fitting the same classifier as I did before with a conformal prediction wrapper. And here are the results. please see that the coverage says, excuse me, the marginal coverage says that it's on average 90%, but the guarantee is not uniform. Look at the digit 5, for example. The coverage is dangerously at 84.1%, and the average size is smallest. Excuse me, average size is the size of the prediction set that we saw before, and we'll be seeing for the whole presentation. The average size measures the specificity of the predictions. And what I mean with that is a smaller size indicates higher confidence from the model. So you would be seeing only one outcome. The more outcomes, the more uncertain is the model. Then again, what I'm trying to say through this image is, through this slide, is that on average is not good enough because we're talking about imbalanced data sets. You would want your minority class to actually have coverage because, come on, this is what conformal prediction is all about, right? You've been talking about coverage for the last 20 minutes. Conditional coverage means that the coverage is guaranteed over all classes or data points, which is not the case where I'm pointing right here. So you can see, although it says the overall code is 90%, it's actually only 80% of the case happening. So I'm empirically testing the same. Now, this is a very stronger guarantee because you say for every specific subgroup, and in fact, every type of input data, the coverage should be correct. In terms of compared to marginal coverage, we just said on average, that's going to be the case. Thankfully, we have a way to deal with that. So that's why I said, please think conformal prediction as a recipe, because if we split the data points that we see, the difference what I have in this slide is the blue letters that I have on the screen, which is per class. So if we split the calibration set per class or per another group of your preference of your data, we can actually calibrate it and approximate, I want to highlight this, conditional coverage. Conditional coverage is something that we as humans in 2025, September, have not found yet a way to guarantee it mathematically, but we can approximate it with a very good approximation. So I'm doing the same step, I'm showcasing the same steps that I did before, with the difference that we're calibrating per class, so I can provide approximate conditional coverage, because I want my minority class to be covered. Again, I want to show you how easy this is with the libraries that I use. Please be mindful that different libraries are using different arguments. They're providing, in a way, different ideas on how to reach an output. But I'm using Krebs 0.8 here, and I'm mentioning 0.10 because things change over time. You can see that what I'm doing, splitting calibration per class, is only an argument which is class conditional equals true. How amazing is that? Reading a lot of papers and just putting an argument, class conditional equals true, it's an amazing abstracted concept. These are the results that we have while fitting the same model, but only with a class condition equals true argument statement in the function. So we can see on the left side of the screen that digit 5 used to be 84.1% covered, where now that we have a label conditional conformal predictor, it's actually 96% of the time that which is covered. I have the average set size next to it on purpose. What I want to illustrate is you can see it goes from 0.691 to 1.4, which means the prediction set is getting bigger. This is the price we pay for protecting the rare classes, and the prediction set will much likely be larger. It contains more plausible value, more possible outcomes to achieve that higher coverage. This is all good, I think, and I do hope. But before you went away and implement something like this in your solution, I want to highlight 3 main things. All of it, what we saw today, depends on exchangeability. The core assumption is that your calibration data and your future data set are exchangeable. Violations like covariate shift or maybe time-dependent features that they change over time lead to invalid coverage. So your coverage goes down the drain. Be very careful of that. The guarantee only holds for data similar to your calibration set. The second one is a nonconformity score. The nonconformity score is a function to see how nonconforming your new point is. Use your imagination. I'm going to say it again. Think conformal prediction as a recipe of steps. Don't think it as an algorithm. Go, try stuff. Change your nonconformity scores. Make it from an absolute error to something else. Try different stuff. Try to see from different ways. Make your own conformal predictors. That's what I'm trying to highlight today. Nonconformity score plays a huge role in an algorithm like that. The choice of it measures, again, how strange a data point is to your calibration set. A poor score or a poor method or a poor approach to that leads to wide or uninformative prediction sets. The score must be meaningful for the task to give margin distance for classification. Lastly, interpretation of prediction sets that we see on the screen. The outputs are sets of plausible values, not single points anymore. For classification, sets can be empty. They can also be wide. They can have one set, but they can also be empty. Empty sets is an amazing opportunity not for you to be more confused, but to have a human in the loop to review your data, to evaluate them and to say, oh, the model is saying, I don't know what to do. Please get an expert, just like we do when we're called. We get an expert to see. I Google, and then I go. But before I do, last slide. I want you to remember what we said today. If you walk out of this room, which is at 11:05, I want you to remember 4 important things. We need more than point predictors. Let's be clear. Conformal prediction is a recipe. Saying the same sentence again, it's not an algorithm. Use that. Use your imagination, change that, optimize for different goals, change that. Data in real life are messy, very messy, if only available. The marginal coverage is not always enough. Although we can be on average correct for many use cases out there, there should be cases that this is not actually the case. Proper example is imbalanced data set. We can find imbalance. And what I mean with the last point is we can rethink imbalance. We can find another way. For years now, researchers have been oversampling, undersampling. Let's try to rethink imbalance. Let's try to think imbalance in a different way, because some things are imbalanced by nature, right? It's not very every day that you have a CT brain scan, you have a tumor when you're 30. This is imbalanced by nature. Maybe it should stay like this. Maybe what we can do to approach this is to actually get a label with coverage. This is a very useful tool. I wish that this presentation you will walk out with understanding that conformal prediction is a recipe, and not like that. Thank you for attending.
Yeah? Do we still have time for questions? 5 minutes? All right, questions, everyone. Should I pass the mic?
Hey, thank you for the presentation. Very, very interesting, and definitely something I would want to have more, like this probability idea of how probable is it. A different spin than I would usually look at, but definitely one I would want. I got a little bit confused at some point when you start first showing the average set sizes, because my expectation was that they would be between 1 and 10, because you at least have 1. But then you said you can have empty sets later in the presentations. And I find that a little bit confusing, because the point is that you should provide a set for which you have 90% likeliness that your answer is inside that set. But with an empty set, there's 0% chance because there is no options there. So how does that work? Can you explain how we get average set size below 1 and how these empty sets work, please, a bit.
Of course. We can definitely touch base later on, and I can elaborate and help you on it. Is this the slide that you were talking about? That's my first question.
Yes, that was the first slide where I got confused with this all 0.9, and I thought it would be, well, I think if it's before you do this set size, I would have expected all ones here, and then in your next iteration, I see 1.4. That makes a lot of sense.
Yeah. So this slide, again, illustrates the difference between having marginal coverage, which is the main benefit of a general conformal prediction framework. And the marginal coverage says that on average, 1 minus alpha, which is your confidence level, of the predicted regions that we see on the screen will contain the true label for new samples. Of course, if I said at some point in the first couple of slides that you can be 10 out of 10 correct, then you can be 8 out of 10 correct, but you can very easily be 0 out of 10 correct. They will have those examples. That's what the empty set is about. Empty set is just the model saying, you know what? I don't know what to do. I don't know the answer. I'm very confused. I don't know what to do. That's what the model says. So instead of saying, because the model says this 90% guaranteed, it just says, look, with 90%, I can show you, I can tell you that I don't know. I'm uncertain. Thank you. Another question. First row. Wow, a lot of questions.
Front row pays off.
Yeah, thank you.
Definitely.
I was wondering, you're very focused here on coverage intervals or coverage sets. In my experience, especially with people that are not so stat savvy in their background, you always get misinterpretation of that. So could this approach be adapted to something like a Bayesian confidence interval and something like that, where the interpretation is a bit less easy to get wrong?
I'm reframing your question because it's difficult to hear with the speakers being on the other side. You say that we can focus our attention more on the coverage than the interpretation of the coverage. Is that? Can you reframe your?
No, I mean, is it necessary that you can you only do this with the output being a covering set, right?
Yeah.
Is there no other something like a actual confidence interval with some prior and posterior to it?
Mm-hmm. So the main, what's different with conformal prediction is the guarantee, and that's why I highlight so much the margin, the guarantee that this is going to be the case on average. Other methods, you named something, other methods like confidence intervals or bootstrapping or Bayesian approaches comes at a cost that Bayesian approaches has an assumption about posterior but also prior distribution. Bootstrapping, there are a couple of papers out there that says that they undermine the variance, apart from the fact that they don't give you coverage. What this method has as an output, what the main benefit of the output is, that this is actually proven to be the case. That's the so strong benefit that if I give you a set, a plausible set of values, which has 4, sticking to MNIST, it's actually 90% of the cases that also empirically, but also theoretically that this is proven. This is called validity. Validity is called the empirically trying to see if this is actually going to be the case. So here, on my first couple of slides, empirically we see that this is actually only 50% of the cases that this is happening, although the model says, you know what, this individual is healthy 9 out of 10 times. For a probability to stand, probability is when you say 90% probability, is actually 9 out of 10 times that this is happening. We don't have time. So I'd like to talk days about it.
Thanks anyways, maybe later.
Yeah.
All right, for more questions, you can find him around because he will be here for 2 days. Let's give him all a final